kind of go back and think about what I've done. And so I try to kind of wear both hats for this talk or this webinar. So being a professor, I thought at least, I hopefully can share some lessons. And having, done various things within IEEE's umbrella, I was also hoping I can share a little bit about, my background, how I ended up in PES, which is not something I planned when I was in grad school. So I'm looking forward to share my story, and I don't know how you guys do with questions. Do we do questions live or do we wait till the end?
It's totally up to you, Matt. So if you are free, if you feel comfortable with questions in between the session, we can do that. We can also have them post questions on the chat on the site, and then we can get to them at the end. Or if you
Okay.
want to do questions at every 20-minute mark, that is perfect too.
Okay. Maybe we can try maybe with live questions and see what happens.
Awesome. I like that.
Okay. All right. Good. All right. So yes, my name is Matt Masalki. I did change the title a little bit. So I think the original title was Being an Entrepreneurial Electrical Engineer. And I realized, with three E's in the title, we're just one I away. So I added basically an I to the beginning. So I'm an entrepreneurial electrical engineer, which is IEEE, like the iPhone. And I'll talk a little bit about my route to academia and how I have basically interplayed with startups along the way. So, for those of you who don't know me necessarily, I did not grow up in the US. So I grew up in Copenhagen, Denmark, which also has a huge energy footprint today, but something I was not particularly interested in at the time. I came to the US when I was 16, and I finished high school in the US, and then I lived in Ohio and Kentucky. And when you live in Ohio and Kentucky, I was looking at the schools, and what I did was I went to the University of Cincinnati, which basically the school closest to me. And I spent, 5 years there. I did a degree in mathematics. I worked a lot on the signals and systems side of electrical engineering, and I'll talk more about this in a bit. And that was a really great experience because I got to kind of think a little bit about how to automating algorithms. Automation in general was pretty fun, making algorithms and computers smart. So I thought I'd go to grad school and study control theory. And I was able to work, well, I'll tell this story as well, but I basically ended up working in power systems, focusing on optimization. And during grad school, I got a good experience to interact with, a real company, a startup company. And I was doing some late night consulting in Michigan. I joined this startup company called Route 3 Technologies. And for those of you in the power industry, you have a good sense of what Route 3 means. So basically, we deal with three-phase systems. So we worked basically with very large commercial industrial energy customers, building software, trying to reduce their costs. After about a year, I moved to the University of Vermont as a professor. I kind of leveraged my startup experience as essentially a postdoc experience. And I was able to get a position at the University of Vermont, where I lead a number of large DOE projects now. And from those DOE projects, we've spun off a company as well called Packetized Energy. And you can see the timeline at the bottom. So what I'll do next is I will basically spend a little time on each of these sections in proportion to basically the time I've spent and the amount of lessons I've learned, and I'll try to share these lessons with you. So at the University of Cincinnati, if I were to say, one thing I learned, or one lesson I learned at the University of Cincinnati was that you can do more than what you already know, right? Which kind of relates to the courses. So a lot of us take a lot of classes, and we think that what we should do is what we've learned in those classes or what we've taken. So the experience I had in my undergraduate was I basically decided that I wanted to do a dual major in mathematics because I really enjoyed math. So what I ended up doing was I took a lot of courses. So whenever I could, I took as many courses as I could. I ended up with something like 300 credit hours, and I only really needed 186 for graduation. And what I realized after the fact was, what I probably should have done was spend less time in courses and more time tinkering and building stuff, playing with software, playing with embedded hardware. That would probably have been more useful use of my time. But I was also lucky because even though I took a lot of courses, the University of Cincinnati is the first university in America where a cooperative education was offered. So they're very proud of this co-op program they have, which allowed me to work basically during my undergraduate for 3 years. So I spent about half the time full-time, half the time part-time in an oscillating fashion. And it was a small research and engineering R&D firm. So there I got to build image processing and signal processing algorithms on medical and Department of Defense applications. And it was in this co-op that basically I learned a lot about image processing. I learned MATLAB programming. I learned pattern detection and classification, which we nowadays call machine learning. So I learned all these things before taking any classes. So basically, in this co-op, I really learned that, if you do something and you do it enough and you study on the side, you don't need classes to do it. You can do a lot more than what you've taken, what you know. So that would be my lessons from the University of Cincinnati. And then what happened was I went to graduate school, and the number one lesson I learned there, which is what a lot of us have learned as well, is change is constant. So you have to learn to adapt. And I'll kind of share this with you because I came from a control theory background. So I joined grad school working on autonomous vehicles, which is pretty far removed from power systems. And then I actually went through my old emails to see what was going on with me at the time, and I saw this beautiful email from April 2009. So in April 2009, I spoke with my friends via email, and I told them, I can't imagine that I'll find this smart grid interesting at all, which is rather ironic because now all I do is work in this smart grid area. But really, I had no intention ever of working in power systems when I went to grad school. I wanted to build robots. I wanted to do autonomous vehicles, maybe drones. And all my coursework was in mathematics and control theory. So I never took a power systems course as a grad student. But what happened was a couple of months later, I started working with Professor Ian Hiskins at the University of Michigan. And he convinced me that optimization was an interesting and complicated field wherein you could really do some nice contributions. So I was really lucky, basically. I got to work on some really fun problems in the smart grid arena or in the power and energy systems. So I worked on multi-energy system modeling, basically understanding how energy conversion and storage processes, so mechanical, thermal processes, are coupling natural gas and electricity, for example. I worked on coordinated EV charging. So how do you charge a lot of EVs under a transformer constraint, for example? And there are now a lot of companies doing that. And then I also worked a lot around, how do we best use our batteries in a power grid, which is also becoming a pretty big thing. But when it comes to entrepreneurial things, I was a little bit jaded with kind of the pure academic work. So in my last year, Ian had a contact, my advisor had a contact where they basically asked if Ian knew anybody with an optimization background. So he pointed in my direction, and I spent my last year of my PhD basically consulting. And I wouldn't say I was Batman, but I definitely didn't sleep a lot that last year. So we had so I moonlighted basically for this small energy startup company that was based in Michigan and Illinois, called Route 3 Technologies, and it was really fun. It was very much about applying optimization tools. I helped, with investor calls, and it was very early stages of the company, so there was a lot of opportunity. And so once I got a chance to work on some of their problems, it was a lot of fun, and it moved very quickly. So that's something I'll get back to in a bit. But just if those of you who don't know what multi-energy systems are, just think of the fact that our energy systems are really coupled. So like electric systems are coupled to natural gas systems through, for example, compressor stations or natural gas power plants. Hydro facilities couple water systems with electric systems, and of course you have solar and wind systems coupling the electric as well. So there's lots of modeling needed, and this is still a pretty ongoing field. EV charging, we all know about transformers and how we want to keep basically want to avoid wear and tear on transformers, so you don't want to overload them too often. So there's some coordination needed when electric vehicles become more prevalent. On the corrective side, it was more around resilience. So how do you use energy storage devices for resilience? And then just like my undergraduate, when I did this consulting, it was essentially like a cooperative education, except this was on a pure startup rather than an engineering R&D firm. So we basically developed this little diagram at the bottom where we integrated forecasts, we had system models, we had requirements from operators in these very large energy plants. And what they wanted to do was they wanted to understand, how do I dispatch my chillers? And how do I dispatch my boilers? And how do I dispatch my combined heat and power plants? And we basically embedded all of these requirements, similar to unit commitment and economic dispatch, into a big optimization problem. And we generated these operator schedules for the human operators, who then implemented it, and then we kept optimizing over and over and over to give them basically guidance on how they should optimize their costs. So this is very similar to the textbook economic dispatch and unit commitment problems. So then what happened was I had a lot of choices after graduation. I was very lucky. I could go to postdocs, which is where a lot of people go, or I could join the startup Route 3 that I'd been with already for a year. And it was it wasn't easy. It was not an easy decision. So my wife sometimes still bugs me about it. But we ended up staying with the startup company. And there I learned a lot in a year. So the lessons I learned were basically deals around, if you're developing a technology and you want investors to buy it, you need some form of scalability. You need a scalable product. So one thing I learned that was critical was scalability requires modularity. What that means is when you develop models or tools, for them to scale, they need to be modular. So plug and play is an important component of that. And also computational costs have to be small. So basically think of it like small packets are important. Legos is a good example of this, right? The other one is, as engineers, we often forget, especially in industry, that when you're working in the field, the technical details sometimes are not the most important things to talk about. So the details of the technical work is not what your boss wants to know. And in many cases, for many of us, so my CEO and most of the folks in the startup company, they were MBAs. So having to communicate with MBAs was a very different experience than having to communicate with your PhD advisor, for example, or your other engineering friends. So that was a really good lesson, was learn to communicate and work with MBA folks. And then the third lesson that I think is really important is we often forget that solving electrical engineering problems, especially if you're trying to bring it to market, you really need good software. And so if you want to develop a technology, you really need to be fluent in some form of software. So whether that means designing the software, writing the software, there are a lot of ways in which software can be made, but really it's important. Software is very important. So those are the three: scalability, software, and learn to communicate effectively with folks that do not have your own background. So what happened was, when Route 3 started out, we were able to raise $1 million from VCs in California, Michigan, and Illinois. So there were some folks in Silicon Valley. So I had, as I mentioned, I did have postdoc offers from a number of fantastic schools. But the idea of being able to work in this very, very dynamic environment and building an actual product that people would use, people being the energy managers at very large commercial industrial energy facilities, was very exciting. And at the core of this software, what we were trying to do was to solve what we call the energy riddle. And this energy riddle deals with the fact that at any given time in an industrial facility, you have weather data coming in, you have pricing signals coming in from maybe your tariffs. Maybe you have dynamic pricing, maybe you have demand charges. You need to track your energy usage. You have a lot of assets you can utilize. You have constraints on those assets and on your system. You have to deal with risk, because very often you use energy to produce very valuable products. So saving $1 on energy while putting a $1 billion manufacturing line at risk is definitely not a good business decision. And then, of course, you have compliance. So you don't want to risk the health or the environmental factors. And what we also did a lot around was when we design software, we want to think about, so this is called the productivity pyramid, which is very common in kind of the agile environments. So whenever you build a product can do many things. Some of those things have low value, which in our case was whenever you deal with large data sets, which is what we dealt with was very large data set coming from these historians that sit at industrial plants. So we basically, in one case, we actually got a suitcase full of paper documents around historical data. And we scanned it in, and we found a source in India that could translate this for us, and we ended up with these massive data sets. So finding and correcting bad data is a very low value piece, but actually solving the energy riddle at the top of the pyramid is really what we wanted to do. So this is helping energy managers navigate these very complex utility tariffs. So that was what we were trying to do. And what we ended up building was actually pretty useful software. We were able to show through different avenues that we could actually save a good amount of money while not jeopardizing product lines. So, I used my optimization background. I delved into a lot of kind of large-scale data analysis or data science. And I helped a lot. I didn't write the software myself, but I helped a lot our software team to kind of understand how do we display information to human operators, what information should they see, and how do we, even the colors are something you would need to discuss with people. So there's a lot of interactions around the software itself. I saw somebody raise the hand, but I don't know what that means.
I think it is one of the participants struggling with the audio setting. I'll help him out.
Okay.
Thanks. It's someone else. Hey Ajay, let me unmute you. Ajay, do you have a question? Oh, probably not.
Okay.
We can proceed.
Okay, thanks. So really, I spent a lot of time doing stuff that I'd never done with my PhD. Right, building software is not something a lot of EEs, do during their school. And also, what I had never done was I had never really worked with these weird devices called chillers and boilers, like compression-driven chillers. There's not a lot of EE courses that cover chillers and boilers and combined heat and power plant, combustion processes, thermal energy storage. So basically, I had a pretty steep learning curve in the beginning. So my nose was stuck in these old ASHRAE handbooks and these ASHRAE journals to basically understand how physically do all these devices work. And you can see here's one picture basically showing some data, and we then use the data and fit models to the data under different operating conditions. It was a huge learning curve. It was a lot of fun. I learned a lot. But what I also learned, too slowly perhaps, was that each customer we brought into the company and started working with, we realized that each customer was unique. Even though they may have similar data, the way that the data was derived, the local control loops on the different chillers, the ways their boilers operated, were all relatively unique. So some had, for example, a controller that changed the flow rate of chilled water rather than the temperature differential across the evaporator and condenser. And that meant that the data had different representations. And it became very complicated to basically capture all the different operating cases. We lost modularity, essentially. And what we learned was that each customer was a research project. And if you know anything about research is not something that is scalable. Every customer needs to customize solutions. So at that point, we started thinking maybe we don't have a scalable approach anymore. And what we also did was we made a mistake, or I made a mistake, and I didn't stop and basically reassess our approach because we were running out of time. So the 1 million you raise, you have to prove certain metrics at the end of a year or so, and we didn't have enough time to basically stop and re-implement a lot of things. So what I learned here was really scalability is key, and you need modularity to be scalable. And if each customer speaks a unique language, and you have to spend time translating this language, it's very expensive. Even if you're using software, the models you're using, it's just too expensive. It's too time consuming. And I'll contrast this a bit later when I talk about packetized energy, where basically we are now enforcing modularity, which gives us scalability. So after about a year, I had spoken with my wife a year when I started the job. We decided that after a year we should assess. And so we did that. And after about a year, joined the University of Vermont as a tenure track faculty. And there, that was also a very different experience. So being a professor versus being a startup warrior, they're very different. So some of the key lessons I learned there was, so what I didn't know, and I don't know how many graduate students realize what a faculty job entails until they're in it. But I certainly found out that a faculty job is like 5 jobs rolled into one, with the benefit that you have the freedom to pursue any interest you want. In my case, electrical engineering interests. What I'm also learning, another lesson I think is valuable, is whereas in the software industry, in a startup setting, software is king or queen. Whereas in research, it's really about mathematics and software, or more around coding, really. So we don't build software product in my group, but we need code that can do large-scale simulations, for example. So you can maybe run away from building software tools, but you still need software that does a good job at simulating systems that you're interested in. So you can validate that your mathematics indeed is worth its while. And then the third bullet I have is, even though you're in academia, I think it's very important to build bridges between academia and industry, because there are certainly times when you feel like there's a very, very wide gap between what academics are doing and what industry is interested in. So those are definitely the 3 key lessons I've been learning at UVM as a professor. So my tenure track experience, if any of you are familiar with the recent image of the black hole, so my experience as a tenure track faculty has basically been this. As an undergraduate, we take courses. Our life is simple. As a graduate student, we take some courses. In my case, I didn't teach, but you do a lot of research. So you basically have 2 roles. You're a student and you're a researcher. And if you go through your years as a graduate student, you're basically just a researcher. Now, as a faculty, suddenly you jump in, and you are now a project manager, you're a teacher, you're a mentor, you're a researcher, and you're also an advisor for a lot of undergraduate students who are where you were. So in my mind, once I joined academia as a faculty, I really crossed like an event horizon, and I had never seen that world before. So, if possible, as a graduate student, I think it's important to see if your advisor will allow you to, somehow gather a few streams of photons before they disappear behind the event horizon. So this is the picture from EHT. So at at the University of Vermont, I've been blessed because when I got there was already an energy systems laboratory. And so this was run by Professor Paul Hines, down in the bottom right, who has been kind of building this laboratory up since he got there about 10 years before I did. And now we've, together with some funding from the Department of Energy, from the National Science Foundation, from industry, and the faculty on the bottom of this picture have really been able to bring in a good number of high quality students who've been doing some really interesting work. And these students are from around the world. So it's been really fantastic experience. So Maharaj Amini recently graduated and is at National Grid. He was my first PhD student. Micah Butkin-Levy was my first master's thesis student, and now he's heading to California to do electric vehicle charging. And so I have Adil and Nawaf remaining in my group, and we're bringing in a few more students next year. And so that'll be a lot of fun, while the other students are also doing really interesting stuff. So it's a really fantastic group, and we certainly, even though Vermont is small, I think the Energy Systems Laboratory, also known as Tesla, the Energy Systems Laboratory. So Tesla at UVM is certainly punching above our weight, which is very awesome. And some of the reasons we've been doing very well at the University of Vermont is really because we have found a way to kind of link with industry. So we have lots of industry research projects where the local utilities, the independent system operators, or the transmission operators are interested in working with us. One of my colleagues has a project with Ford around, improving the efficiency of engines through control theory. We have other projects around software development. We have federal partners with ARPA-E, the Sunshot Initiative, and the National Science Foundation. And we recently have a good relationship with the National Institute of Standards and Technology at NIST. So they had a workshop with us this past week, which was really fun. Very industry focused. So I think we've been able to kind of merge the federal funding with industry interests and really kind of hit a sweet spot at understanding, what is it industry needs and how can we, with our skills in power systems, optimization, and control, help answer some questions that are difficult to do without us. So we've been able to garner some pretty good amount of publicity around our projects. So here's, for example, a screen capture of some of the news stories around our ARPA-E project, which is what we call this is the packetized energy management scheme. So you can see in Green Tech Media we made it, in Utility Dive we've been, local public radio, and also in the TV channels as well. So it's been really fun kind of being part of this wave, and I'm certainly not alone in this, right? So I have a team, and that team is Tesla, our energy systems laboratory. And to kind of enforce this industry connection, we've also built an industrial advisory board for this project. So this packetized energy management project, we really built an industrial advisory board of utility partners, you can see here in the middle. We have solution providers in the center, and we also have government and policy operators as well. Because anyone who's worked in power and energy knows that you can't solve any real problems in power and energy alone. Right? So power systems, any problem in there requires, behavioral folks, you need policy folks, you need markets folks. You need a lot of different people than just a scientist or a researcher or an engineer. So maybe it's too bad engineers can't solve all problems, but at least we can communicate with folks with MBAs, right? So then what we've done is, with our professor hats on, we spent some time working with industry on these projects, and we realized that, I guess we didn't have to realize it too much. It's pretty obvious that there are three key challenges facing a lot of, a lot of the power system today. And one is that you have this increasing need for demand that can follow the variable supply. So like solar and wind is coming. We have an aging infrastructure in place, which means upgrading certain components is becoming very expensive or cost prohibitive. And then we have sudden growth in these smart appliances. So there's lots of solar being generated at local places. We're having a lot of smart appliances because connectivity is becoming ubiquitous. So what we're trying to do with packetized energy is we're trying to look at it from the perspective of, state policies in the US and across the world are really pushing a clean energy agenda. And what that means is that we are trying to get this power system to operate as much clean energy as possible. So if you followed like Mark Jacobs, for example, I think he publishes like 50 papers around how to enable 100% clean energy infrastructure. So 100% clean energy is coming. Connectivity is becoming ubiquitous through cheap Internet of Things. Sensors have dropped dramatically in prices over the last number of years. And what we're trying to do at Packetize is really connecting the fact that devices are becoming connected with coordination algorithms or control algorithms that turn these connected things into what we call virtual batteries. And I'll explain what that is in a second. And we're hoping that these virtual batteries can then help make it much more efficient to integrate high levels of renewable generation. So, I don't know how many are familiar with Vermont, but I'm sure most of you have heard of California and their duck curve, or the so-called duck curve. So in Vermont, we have surprisingly high levels of solar penetration. And you can see this from different days in April for the last 4 years. Right? So the purple curve here is an overcast day, which means there's not a lot of sunshine. And then you can see for sunny days in April, in 15, 16, 17, 18, you can see the effect of solar is pretty apparent. So, I think in Vermont, we certainly have our own version of the duck curve. And seeing the solar noon, around, the peak solar conditions, we are below nighttime loads, which is pretty fantastic. It's also a little bit frightening because system operators have to deal with the uncertainty associated with solar. And what's also going on in some of these places are utility programs around these demand response programs. So we have about 15,000 electric water heaters in Vermont, and you can see the effects of these water heaters on some of these grid conditions. So if you are a system operator working on power systems, you know that from any 2 days it can look like this, right? So here in the blue you have in red you have Monday, and in blue you have a Tuesday. This is in 2019 data. So if you know that from day to day you can change this much, which is about a 50% change in demand at peak conditions, it's very frightening. So what we need technology, we need tools. So batteries is one, but they're very expensive. We need tools to basically help overcome this challenge. Right? So one way to do this is we basically install more natural gas. Right? We could do this. We know how to build natural gas plants. We know how to control them. We've done this for about 100 years. But under most circumstances, it's fairly expensive to build. You have to upgrade certain infrastructures to do so, and there are emissions associated with those plants. So in part of Vermont, especially if you have more and more solar and renewables, these devices that sit in people's homes, like electric water heaters, soon to be electric vehicles, and even devices like Tesla's Powerwalls or Enphase's AC batteries, are devices that could be, in a sense, coordinated. And they're already there, so why can't we use them for these flexibility purposes? So what if we could coordinate them? Take lots of these devices, not a single home, but many homes. And then we can start to ask, how do these loads behave when you aggregate them? How well can we coordinate them? And how do we make sure that people who have air conditioners or water heaters still get to use those devices within their limits, right? We don't want to give people cold showers, and we don't want people sitting there and sweating in their homes because we're helping the grid. So how do we do it without being uncomfortable? So the way we do it at Packetize is we basically leverage ideas that run the internet, right? So when you send a file across the internet, what you see is, that big file doesn't make its way across the internet in one piece. It gets chopped up into small data packets. And in the same way, these data packets are chopped up into, these files are chopped up into small data packets, like TCP/IP, for example. We could take demand, which is a water heater demand, and we could chop it up into small, couple minutes of usage rather than a 20-minute heating period. And then what we do is we also leverage randomization in the control to ensure that devices aren't all being turned on or off at the same time. So that creates so-called oscillations. So synchronization of devices is risky, especially in these kind of large-scale DERs cases. So as a system operator, what you want to do is you want to manage the supply and demand. And we know that operating conditions for power systems should be supply equals demand at all times, right? That's how frequency is maintained at 60 hertz. So what happens when you have uncoordinated demand and supply? So when the sun shines and you use energy more or less as you want, there's a mismatch. So we could packetize that mismatch. We can packetize it, and then what we would love to do is we'd love to schedule these red packets to fit in the valley, in the middle, and on the sides. But to do that, you either have to schedule it, which means you have to tell people how to use energy, or you develop a real-time control scheme, which is what we've done, to basically shuffle these devices in place over time. So when you use packetized energy management, your demand will go from what you saw before to something like this. So we're not scheduling individual devices, we're just shifting their use in time ever so slightly. And by doing this shifting in time ever so slightly, what we can do is we can start to track a supply. So we can make demand track supply, which is the opposite of how power systems operate today. And by doing that, we can basically effectively track a dispatch schedule, so it looks like a virtual power plant or a virtual battery. So this is just like you would use a battery, right? You would charge and discharge during certain times to match supply and demand. So what we've done is we've choreographed these packets, and we do this in real time. And that's kind of the secret sauce to packetized energy management, is this real-time scheduling of devices that are being prioritized through this randomization element that we have. So we can show, for example, here, we have so Adil, one of my students, implemented our algorithms on a real-time dynamic simulator. So this was an Opal RT. And in Opal RT, we basically implemented our packetized scheme for about 5,000 or 10,000 devices. And then what we did was we wanted to track this. We wanted to track the red balancing signal with our fleet of water heaters in this case. So on the top, you can see that tracking is pretty good. Like, we can track a signal in real time. And what we can also do is we can do so while maintaining that everyone has a hot water heater. What that means is nobody gets a cold shower. And so, what happens is you go from a demand profile where the device is on the y-axis and time on the x-axis. You go from something like big, bulky, or long on or off times with standard conventional thermostats, and then under the packetized concept, your devices are basically multiple short on-off times. And this is this is what I mean by modular. Right? So we've taken all these devices and we've turned them into small, basically energy packets. And if we can then schedule these small packets and they all look the same to the controller, which means we don't care if it's a packet coming from a battery, an electric vehicle, or water heater, or an air conditioner, we don't care. Because the controller, all it sees are packets. So basically we've created, from chaos being all these different devices, we have created a common language across the devices that all speak the same thing, which means we just need one controller for coordinating across these different devices. And that controller is the packetized energy management controller. And so we've shown, we can play all kinds of simulations with this, but we've shown that, as you have more and more diverse devices in play, you can gather greater levels of flexibility from this. Right? So just like society benefits from flexibility, so does energy management. So you can see here in the black represents a water heater only virtual battery or virtual power plant. And you can see that the green, the diverse virtual power plant, does a better job tracking this red reference than the black one does. So that you can basically see that diversity is key to unlocking some of these flexibilities, which is good. So a common language, diverse populations of devices, and a single controller. So we also have a video here that can show you the real-time tracking behavior. So on the top plot, you'll see the tracking. The blue line represents our reference, and red is the power. And it's just offset for graphical purposes. So there was no prediction or anything like this. This is real-time control. And then at the bottom, what you see are the histograms for 5,000 water heaters. And all we want to show is that, look, when we do this control, we're not going to drive the population up and down like crazy. So what you'll see is a fairly steady state distribution forming while we're tracking this the timescale for scheduling. So this is real time. So this means each device has their own clock. So I think Hasala asked a question, what the timescale is. So what time per packet? So each packet is about 3 to 5 minutes long whenever they consume. And the timescale for scheduling is real time. So each device will basically request a packet on their own clock. So this is a parallel implementation, basically, of 5,000 devices. So you can take a look at this. So in red, we're tracking. And the blue is the signal we're trying to track. And as I said, these are aligned in time. It's just for graphical purposes. So tracking works really well, but notice that the distribution has stopped moving. So now we reach a steady state distribution, even though our power signal is actually tracking quite a bit. So we have flexibility without sacrificing comfort. And I think that's very important. If we want to develop anything at scale, we can't ask people to sacrifice comfort because people are very bad at changing their behaviors. Okay, so let's see. How do I get to the next page? Okay, so basically what packetized energy management allows us to do is it allows us to turn homes or neighborhoods or distribution feeders or even cities at the transmission scale into virtual batteries. And what we've shown through numerous calculations and preliminary results is that the flexibility we can generate, or the scale of these virtual batteries. So for the same level of flexibility, it's about half the cost of a physical battery with the same kilowatt hour rating. So this means that if you use packetize at scale, you can develop these flexible solutions at about half the cost of a physical battery, which is pretty fantastic. So then what you can do is, now you have these virtual batteries, you can start to answer questions around, how should I deal with multiple virtual batteries in a large distribution feeder? How do I deal with multiple virtual batteries on a transmission system? And all those are questions that we're answering in my research group. So, one approach we're taking is, we all know how wide area control works. So frequency regulation is basically a primary, secondary, tertiary scheme that looks at, the primary control is real-time, local control. Secondary control is regional and at a second-by-second time scale, a slightly slower time scale. And tertiary control are economic dispatch at minutely time scales. So and it's global, so it's system-wide. So you kind of have this spatial temporal decomposition for frequency control. So what we're proposing for distribution systems, these advanced distribution systems that manage virtual batteries, is really this power-based control that mimics the wide area control we've seen in frequency regulation. So you can think of basically these virtual batteries making up homes and neighborhoods, and then you aggregate them up through the feeder all the way up to the market itself. So in this case, you have to manage you have to manage resources dynamically, which you could do with packetized or other approaches. You need to manage the grid physics optimally, which means you don't want to violate voltage constraints, for example. You don't want to violate your ANSI standards. And then you have to manage the resource economically so that there is a business case to make this work. And so you can kind of, what we've done is we basically mimic this wide area control problem, and we can look at these different timescales for control in the blue. So the blue block is a control block. The green block, the feeder operational layer, is a optimization block, and the last bit, the grid market layer, is a market block. So we've shown that this approach is starting to work pretty well. There are certain technical challenges that we're working on in my research group. Another thing we're doing, once you have these virtual batteries in place, so once you speak with utilities about it, very often they'll ask you something like, well, where should I put this virtual battery? Where should I put my batteries? Where should I put these EV charging stations? So for that purpose, what we've been doing is, together with Pavan in the Energy Systems Laboratory, what we've been doing is we've been developing software. So software that's usable, or essentially will be usable by utilities themselves to create and answer what-if scenarios. So there we can take, AMI data, we can take SCADA data, and we can take equipment and network data like SIME or EDD or DO, or any of these, utility packages. We can combine the data with the models to create these simulators in GridLabD, for example, or OpenDSS. And then we can do optimization, model reduction, and we can visualize the results in a way that's meaningful to operators. So here you can see, for example, so this is a neighborhood in Vermont. And you can see we get full three-phase information from our simulations. And utility operators can simply plug in a location of different what-if scenarios and see what effect that has on current flows and voltages in different parts of this three-phase network. So I just want to check how much time I have before. Okay, 10 minutes or so. So then if you go back and say, well, how do we grade our packetized technology? So we can build cool software, we can do real-time algorithms, we can dispatch these virtual batteries, we can help the utility solve lots of problems. So how do we pitch the technology? So the way we look at it is, what's the value we can provide to a utility or a market operator? What's the cost to deploy our product? And how do we impact the consumers? And we believe that packetized is one of the few technologies out there that can kind of hit the sweet spot across the board. So specifically, we can provide, because it's a real-time system, we can really hit value segments, value propositions across the different timescales of markets, from peak to arbitrage to regulation. We come in at about half the cost of the standard battery solutions that utilities are starting to purchase. So we believe we have a positive value proposition. And then in addition to this, we guarantee comfort to the individual. So we don't provide inconvenience to consumers. There's no discomfort from having their devices packetized. So I can show you here some data from, this is the real world data. So not simulation, it's not Opal RT, this is real data. This is also raw data, which is, why the blue is slightly, I guess, packetized, you could say, quantized. So what you see here is basically we have a peak condition from 3 to 9 that the utility chose. So this is at a utility, the Vermont Electric Co-op. And we have about 60 water heaters at the time. This was last year. And now we're close to 200. So we have about 6 hours where we hold the peak. And then we have a post-event recovery where we control the rate of recovery, and then we can return to what we call load shaper. So the question around the cost, how much it costs to upgrade the equipment. So when I said it was half the cost of batteries, that included the retrofit cost and the online and the data transfer cost as well. So this includes everything. So I think the retrofit for a water heater is like $150 for the equipment for a single water heater, and you need about 2,500 water heaters to get a megawatt of flexibility, plus minus flexibility. So these costs are all included when you compare to the water heater, to the battery. Okay. So then what we can also do is we can, because it's real time, you can integrate real time prices. So if you have ISO prices, which in New York, in ISO New England we have, so every 5 minutes prices are updated. So we can basically respond to these prices so that when the price is high, we go low, so power goes down. So you buy low and you sell high. And when the price is high, you essentially discharge from your virtual battery. When the price is low, you charge with your virtual battery. And charging just means consume more than some baseline. And these are not just water heaters. So we have deployed electric vehicle chargers. We've tested HVAC thermostats. We've tested grid edge batteries, and we've tested PV inverters as well. So there are lots of products that can be packetized, which are relatively large appliances, which can help a lot for the utilities. So I'm running out a little bit of time, so I just want to catch up a little bit. So some of the key advantages that packetized energy management inherits is that it's a smart, you set it and forget it, which means you don't need to constantly ping or remind consumers or utilities of what's going on. So there's no decisions to make because we don't compromise comfort. Because ideas are borrowed from how the internet operates, we have basically modularity built into it. Right? This notion of packets being the mechanism through which we control means every device speaks the same language. Every device is modular, it's plug and play. So scalability is inherent to the product and technology itself. We guarantee comfort, and then because we actually develop our own hardware for this first round of the company, we have complete control, just like Apple does with their suite of hardware. We have complete control of the hardware, the software, and the data transfer, which means we've built in some pretty cool, we basically have hardware encryption at the device level, and we have state-of-the-art TLS 1.2 cybersecurity guarantees at the cyber level. So we've focused a lot on making sure that our cybersecurity concerns are in check, because that's a very important topic, cybersecurity. So just to show a little bit of a diagram of on the startup side where we've been. So some of the ideas for packetized were developed by Paul Hines and Jeff Froelich around electric vehicle charging. Then when I joined University of Vermont, I wrote the proposal for the ARPA-E project, which was funded. And when that was funded, the company was generated in parallel, and we submitted different disclosures for patents. We've launched 2 projects in 2017. We launched 2 more projects in 2018. And we were recently honored with a CB Insight, naming us one of the game-changing startups of 2019. So certainly we've had a lot of fantastic partners along the way, which has been very helpful. So being in Vermont helps a lot because you have forward-leaning utilities. And you can see there the blue device right there is our water heater thermostat, which we call the Mellow because it mellows out the grid, I guess, or it looks a little bit like a blue marshmallow. So just to finish up, I think it's important, to realize that the stuff you do, the stuff you think you'll do, and the stuff you actually do can be very different. So, when I said in April 2009, I said I can't imagine I'll find this smart grid interesting at all. I'm certainly happy to say that I was extremely wrong on that account. And I am very much enjoying working in the smart grid arena on many different projects with many fantastic people. And it's I'm definitely blessed to be able to do so. And then also, I don't do it alone, whether it's at home or at work. So my wife at home definitely makes this possible. So she supports me through thick and thin, and definitely has been a lot of rough periods. And so, working day and night. So these batteries I have, these kits, they never run out of batteries. So maybe we should just find a way to manage children's energy. I saw the 2 questions posted. And I will answer this now. There are a couple questions now. Okay. I'll answer these questions, but let me just make one brief announcement. So at the upcoming PES General Meeting, if any of you are attending, I have 3 sessions that I'm chairing around distribution optimization problems. We're looking at advanced grid operations with DERs, and then advanced grid architectures to support scalable DER integration. We have an opening for a postdoc in my group, so if anyone knows of people finishing up their PhDs, interested in modeling distributed energy resources and controlling them, we're certainly looking. And I think that's the end of my show. Okay, so let me answer some questions. Let's see. Can you explain how the high peak is shifted by doing the packetized optimization? How that peak load is satisfied? So how high peak is shifted by doing the packetized optimization. So the way packetized works is by having the devices themselves. No, I have not. So Mohammed Rasul, somebody asked about research on small modular reactors. So I've not worked on small modular reactors, nor microgrids. And I assume by reactor you mean small nuclear reactors or something like this. Can devices have a priority for scheduling? So yes, that is possible. So right now the priority is embedded in a local measurement. So each device, we basically provide a little bit of smarts at the device level, and the devices are able to understand what their energy need is. There's some good questions coming in now. Can't keep track. Okay, so devices can be scheduled. Devices can be scheduled based on priority. So one of the key pieces to packetized energy management is the fact that we put smarts at the device level as well. So the devices are essentially aware of their local energy need, and this awareness of their local energy need and the fact that they want to guarantee comfort, which means they want to stay within some energy bounds, is what drives their priority first. We have been looking at, you can override priorities. You can basically say that anyone that is not needy, anyone that does not need energy badly, can be essentially blocked from requesting. So that's something we could do. So yes, you can do priorities for scheduling. The next decision is based on current data. How does time lag? So what I showed you here regarding time lag. So on the cyber side, these are actual with delays. So the delays are on the order of 500 milliseconds. And because our implementation is asynchronous, basically as requests come in, we have not seen any evidence that time delays of the order of a second or less is actually affecting us at all. Now, if we're doing frequency regulation, that might be different. So that's something we're researching right now and going to continue to research for a while. Let's see. No, React is getting funds for starting. So the most challenging part of any startup is funding. Usually you don't start a company unless the technical part is relatively sound. So that has been that is a big part. So funding is difficult. The technical part, like if you go look at any company that does, cool technology, most of the time the technical components are relatively simple. Um, so like Google's like when Google started out, they crawled spiders across the web to figure out what websites should be connected to which websites. So the technical part is not hard. Convincing the venture capitalists that your market is there is the most difficult part. So convincing people that there's a market for something before the market really exists is the key part. When did you start actually PES? So I joined PES, I think 2010, 11, when my advisor asked me to attend PES general meeting. I think it's 2010. I think it's 2010. So this biggest challenge is it's fundraising and hiring. It's the biggest challenge we have. So hiring people, it means you have to hire very high quality individuals, and you have to have the right team composition so that working with less money is something that everyone can do. So you need people that are willing to sacrifice short-term benefits for long-term opportunities. So hiring is important. Let's see. It's going really fast, these questions, so I can't keep track of the... okay, let's see. To communicate with an MBA. So an example of how to communicate with an MBA. If you go to, so this was a good example. One time I had developed, at Route 3, I had developed an optimization model that had some really nice properties. And I was able to prove mathematically that the system would perform, the simplified model would perform as well as the more complicated one, would perform equivalent. I was very excited. So I went to basically present this to the CEO of the company, and the CEO basically started glazing his eyes over when I started explaining how cool this equivalent formulation was and how the proof held up. And he said, wait, stop. Why do I care that this proof is equivalent? And I told him that now we can solve the problem, half the time and get the same solution. He was like, okay, thank you. So explaining the details of a technical modeling component versus telling your MBA boss that, look, this will help solve the problem in half the time without sacrificing any of the savings. That was the example that I would give. So that was a real one. Let's see. Regarding cybersecurity, how do you overcome challenges of security methods implemented? So right now, so cybersecurity is very important, and there are not a lot of standards necessarily developed for these Internet of Things. So Amazon Web Services has certain standards associated with managing with AWS. So that's TLS 1.2. And then we have hardware level encryption on the devices, which are kind of an IoT. It's certainly over the top for now, but it helps prevent basically wide scale hacking of our devices. So there's a hardware level encryption is pretty powerful. What else do we have regarding cybersecurity? If the grid goes down, the utility will lose profit. If grid investment goes down, how do you get a utility to be supportive? Grid investment goes down in a traditional setting, utility lose profit. If grid investment goes down, I'm not sure exactly. Oh, there's another question follow up. So grid investment goes down. So I think the way we speak with utilities is more around, we can help them manage, for example, large transformer stations. So if they're seeing load growth, like they did in New York when they had the Brooklyns and Queens demand market, BQDM, there we can help basically shape the load so that you don't overload your current assets, like transformer limits, for example, power limits. So there our argument is, look, you don't have to upgrade your costs. It's a lot of so many questions. I don't know how I can answer all these questions. Um, so somebody asked if they recommend that they should learn about the smart grid. Yeah, I think it's a good idea to be aware of what the smart grid is, but it means a lot of things. So there are many ways you can learn about the smart grid. Um, so there are lots of fantastic podcasts that are out there. The Energy Gang is a good one that touches on a lot of technology, markets, and policy questions around the smart grid. And then as long as you're good at circuits, you can pick up power systems whenever you need to. So if you know circuits, you know power systems just with a different language. So that's a good one. To get utilities to be supportive, what you need is you need a way to scale deployment, and you need a way to make your installs very quick and pain-free. There are a lot of opportunities for startups in embedded systems and IoT. Like I said, the sensors are dropping like crazy in price. So I think buildings is a big spot where there's a lot of room for innovation. So like large scale commercial buildings. If you can embed lots of distributed sensors to gather lots of data, you can turn that data into, with machine learning, you can turn that into all kinds of wonderful products. So I think, real-time sensing is a big deal. Data gathering is a big deal. There's a lot of opportunities around efficiency, scalability, future EV penetrations, and then again, ban traditional car making. I don't see any obstacles to scalability of future EV penetration. So there are some concerns around lithium-ion, cobalt, lithium-ion batteries in general. There are some concerns around those at global scales, but not a big deal right now. Any day. Yes. Yep. Yes. So AJ Kumar asked a good question around which the Internet of Things are becoming prevalent, sensors are becoming cheaper, so connectivity is becoming ubiquitous. So the probability of getting hacked, the probability of one device not being very secure is very likely. So cybersecurity is a real concern. I just today saw that a number of companies around autonomous drones are being deployed, and for some reason there, cybersecurity seems to be less of a problem. Cybersecurity is a real concern. Utilities around the U.S. are certainly being hit by national actors around the world. So those things are happening, but utilities are very diligent in their cybersecurity practices. We don't see a lot of outcome from it. Ali Asgard asked about discharging a virtual battery. How do you discharge a virtual battery? The way you discharge a virtual battery means you have a baseline to it. Charging and discharging virtual batteries is all about a baseline. So if my normal population of water heaters consume X, and I'm currently consuming less than X, then I'm essentially discharging the battery because I'm providing the devices less energy than they would need under normal circumstances. If I'm providing them more than X, then I'm essentially heating up the water heaters. I'm providing them more energy than they need under normal circumstances. So it's all about a baseline. What are the automatic monitoring softwares used in packetized energy? I don't know what you mean by automatic monitoring software. So we have software running in the cloud that is real time. So it runs with AWS. So there's an implementation there that's fairly clever and very lightweight. So that I don't know what else I can say on the automatic monitoring. I think those are the and we use yeah. So okay. We use SCADA. So the SCADA. So SCADA systems take in the grid measurements. So in packetized energy, we're not tied in with SCADA, if that's what you mean. We're not tied in with SCADA. We run separately for now. I think the cybersecurity concern has to be overcome first. Around the working principles behind virtual batteries, it's really about the physics of the devices that you have. So if you take a look at air conditioners and water heaters, the physics of air conditioners and water heaters are as you heat up water or as you cool down a room, you are approaching a certain temperature limit. So for water heaters, as you heat up a lot of water heaters, they are approaching their upper temperature limits. And if they approach the upper temperature limits, then less devices are available to be turned on because they're all sitting at their upper limit. Essentially, your virtual battery becomes full if all your water heaters are at their upper limit. Your virtual battery becomes empty when all the water heaters are at their lower limit, which means you have to turn on water heaters. You have to start charging, essentially. Um, the current challenges, so the number one challenge right now is we have a cool real-time system. The next step is to develop a accurate real-time estimate of basically actual battery parameters. So I talk about the virtual battery, but I never show you the state of charge. So making virtual batteries look like real batteries, that's the main technical challenge. The non-technical component is to finish a fundraising. So our company is working very hard to maintain our current projects while driving our fundraising efforts to a positive resolution. The max sizing, so that we have tested our virtual battery software for thousands of devices without incurring any major limits at all with our AWS implementation. If that's what you mean. So what Nayu is asking a very good question around how do I know essentially what I can and cannot track? How do I know what I can and cannot do? That's a very important question. So that goes along with making virtual batteries look like real batteries. So if I can estimate in real time what the actual state of charge is, if I can estimate exactly what all the parameters are for this virtual battery, then I can dispatch it into market and I have certain certainty that I can meet the demands in real time. So right now we're focusing on peak response, peak demand reductions, and arbitrage around locational marginal prices. And the next step is frequency regulation, where it's very important to know the maximum size of your battery, or essentially what family of regulation signals can I track, and what family of regulation signals can I not track, and that gives rise to your parameters. So that's something we're working on with the other project that I showed earlier with the spatial temporal decomposition. Okay, I think I've tried to answer most of the questions. If there are any last questions, I'm happy to answer those. Um, Otherwise, I'm happy to wish everyone a good weekend. Okay. It's so now you keeps asking very good questions. So the physical model of the device. So remember the one thing we did for this technology is that we've basically turned all the devices to look the same to the controller, which means a data-driven approach is quite powerful. And if we were to integrate the physical equipment, the physical model of a device, we would need to know what the devices are providing these requests or these packets, basically. So that there's a nice trade-off now between having basically a single language between all devices that all speak packetized and starting to differentiate which device is which device to model them. So we're looking into both. We're looking at if I know the device type, in addition to the requests, then I can create essentially a language. There's a packetized language equivalent for water heaters, packetized air conditioners, packetized electric vehicles, and packetized battery storage devices. No, so Ali Asghar asked a good question. So the cool thing about the water heater thermostat control is we don't control the bounds on the thermostat. So the customer decide what their thermostat bounds are, and we just stay within those bounds. So thank you. Yeah, the kids' energy levels need to be managed. So thank you, everyone. Have a great weekend.
Thanks a lot,
And
Matt.
thank you, Bala. And thank you
Hey,
too for,
everyone. Mhm.
thanks Hasala and Bala for driving this fantastic IEEE PES community. And I'm proud to be part of the YP for a few more years.
We're glad to host you today. And everyone, if you have more questions, feel free to reach out to Matt. Matt, I hope you don't mind them reaching out to you over LinkedIn or other social
Nope.
media networks, except Facebook, right?
Nope. Please do. Yeah, I'm happy to connect on LinkedIn or Twitter. Yeah. All right. Take care, everyone. Have a good weekend.
Awesome. Bye bye, guys.
Bye, everyone.